In problem 72, we have this cylinder and also we have this mass. They are connected together with this cable. The question says there is not going to be a slip between this roller and this incline, so it's going to just roll up without any slip here. And so it means the friction is enough to tolerate the friction force, so it's not going to be a slip. And the question is, what is the angular acceleration of the cylinder? If I assume the angular acceleration is alpha in clockwise, then what's going to be this angular acceleration? And what is the minimum friction coefficient between the cylinder and incline to have no slip? So first of all, like any other problem, we are going to have free body diagram. In this one, we are going to have two free body diagrams, one for this one and the other one for this. So for this one, if I wanted to write here, we are going to have tension of the cable and mass of it times G, 10 times G, the weight. For this one, the tension is going to be the same. We have this tension, we have normal force, and also we have friction. If you don't know what is the direction of the friction, you can assume anything you want. You can assume it is upward too. But at the end, if it turns out to be negative, it means the number is correct, but it is in the other direction. And also we have mg. It is 7 kilogram, so 7 times g. And we can write Newton equation for both of these. But before doing that, let's talk a little bit about the kinematics here. So because there is no slip here, the acceleration of the centroid is going to be r times alpha. And also acceleration of the cable is going to be 2r times alpha. The way you can find it, you can say, for example, the tangential part of the acceleration of this point of the disk is going to be acceleration of O plus alpha cross r. So I'm going to have r alpha plus another r alpha. So acceleration of the cable is going to be 2r alpha. And same thing for this one, because they are connected with the cable together. Acceleration here is going to be downward with a magnitude of 2 times r times alpha. And knowing this from the kinematics of the problem, now we can use Newton equations for any of these two. For the cylinder, we have, let's say this is x direction, this is y direction. Sum of the forces in the x direction is equal to mass times acceleration of the centroid in the x direction. So in the x direction we have t minus f and minus 7g times sine of this angle. It is 20, let's call it theta for now. So I'm gonna have negative 7g times sine of theta is equal to mass times acceleration, which is r times alpha. In this one, in this equation, we have t, f, and alpha unknowns, 3 unknowns. Sum of the forces in the y direction is equal to 0 because there is no movement in the y direction. So n is going to be equal to 7g times cosine of theta from this equation. So we got the normal force. We had only one unknown in this equation and one equation, right? So we are going to find this unknown, which is n. And some of the moments about the centroid is going to be I about the centroid times alpha. Because I assumed alpha is in clockwise, I'm going to assume clockwise is my positive direction. Moment of n and weight about O, they are 0. You're not making any moment about point O. Moment of t is going to be t times radius in clockwise direction. Moment of friction is going to be f times radius in the clockwise direction. So together we're going to have friction plus t times r. That's going to be the total moment. It is equal to I of a cylinder about the axis of it is 1/2 of its mass times radius squared times alpha. So in this one we have 1, 2, and 3 unknowns. So together this one and this one we have 3 unknowns but 2 equations, right? So we need one more equation, and that equation comes from this one, from this mass. So for this one, if I call, for example, this direction as, I don't know, you can call it Z, for example. Sum of the forces in the Z direction is equal to mass times acceleration of this mass. In the Z direction, we have weight of this guy minus tension of the cable. It's equal to its mass times acceleration, which is 2r times alpha. So times 2 times r alpha. R is given, R is equal to 0.15 meter, and also theta is equal to 20 degree in these equations. Now I have 1, 2, and 3 equations and 3 unknowns, f, t, and alpha. So I should be able to solve them, right? So if you do that linear, solve these linear equations, you're gonna find alpha is equal to 22.8 radian per second square. So it turned out to be positive. It means our assumption is correct. So if you assume from the beginning alpha is in the other direction, that's absolutely fine, but your alpha is going to turn out to be negative. It means actually it is in clockwise, right? So you have that option too. Friction force is going to be negative 17.73, which means the actual direction of the friction is upward. So again, nothing is wrong here. The only meaning of this negative number is it is negative in this direction, which means actually it is upward. That's all. So we don't need to change anything, and everything is correct. And also the tension of the cable is going to turn out to be 29.7 Newton, and also the normal force, which we got it here, is going to be 64.5 Newton. And the minimum required friction coefficient means it should be about to sleep, right? So that's the minimum coefficient that we need, minimum friction coefficient. In that condition, friction coefficient is going to be F divided by the normal force, actually the absolute value of them, right? Which is going to be 17.73 divided by 64.5. So mu s is going to be equal to 0.275, and it doesn't have any units. So these are our solutions.